Hello, my dear friends. We have reached the last part of integrals. So far, we have completed indefinite integrals. That means I have taught you different methods for calculating indefinite integrals. I talked about the substitution method. I covered trigonometric substitution. I covered integration by parts. I covered partial fraction decomposition. And we also reviewed trigonometric integrals together in a special lesson. Today, we're going to see why we studied all these indefinite integral methods. Today, we're going to introduce the concept of definite integrals. We'll get right into it and work through it together. Definite integrals. Why did definite integrals even come into being? To find the area under a curve. Well, we could already find the area of many shapes before. You could do that too. You know how to find the area of a circle, a triangle, a trapezoid, a rectangle, and a square. But we want to be able to find the area under any curve, whether it comes from a geometric shape or not, whether it is convex or non-convex. This is where one of the applications of integral calculus and perhaps its main application comes into play. Now, let's look at the concept of the definite integral. As you can see, the definite integral represents the area between the function and the x-axis. If the curve is above the x-axis, we consider that area positive. And if the curve is below the x-axis, we assign a negative value to that area. This is essentially the idea behind the definite integral. Until now, whenever we calculate an integral, we never specified any limits for it. We simply wrote the integral sign, then the function, and then dx. But in a definite integral, we now have specific limits of integration. This means we write two numbers, one below and one above the integral sign. This represents the signed area between the curve of the function and the x-axis from the lower x value, which is the bottom number, up to the upper x value. Now, let's go over its rules. Consider the definite integral from a to b of f of x dx. As you can see, three different regions are formed here. They are labeled as capital A, capital B, and capital C. For regions A and C, since they are above the x-axis, we assign positive values to their areas. But for region B, since it is below the x-axis, we assign a negative value. Excellent. Now let's move on to the fundamental rules. Rules of integration, or the laws of definite integrals. The first one, the integral from a to a of any function is 0. I think that's pretty clear. It means the area between a function and the x-axis from a to a has no width, so there is no area. Therefore, it becomes 0. Let's move on to the second rule. The integral from a to b represents the area between the curve of the function and the x-axis. For different reasons, for example, when calculating the integral of an absolute value function, a greatest integer function, or other types of functions that you will see soon, we may need to break the integral into smaller parts. The integral from a to b can be broken into n different parts. These parts do not have to be equal. They can have any length or size we need. But here, for example, we have divided it into two parts. We said the integral from a to b can be written as the integral from a to c plus the integral from c to b. Does c necessarily have to be between a and b? Contrary to what you might think, no, it doesn't exactly. C doesn't even have to be between a and b. Later, as I said, we'll see examples. But it can be divided into n parts. The important point is this. If you go from A to C, then you must continue from C to B. You cannot change the order of B and C. Excellent. Now let's move on to the next point. The integral from A to B of f of x dx. Usually, we place the smaller number at the bottom and the larger number at the top. For example, we say the integral from 2 to 5. We usually don't say from 5 to 2. But if for some reason in a problem we need to swap the positions of these two numbers, these two limits, what should we do? Nothing special. We just place a negative sign in front of the integral. This means the integral from a to b of f of x dx is the negative of the integral from b to a of f of x dx. These are the essential tools that I use again and again when solving different problems. Now let's move on to the next rule. The next rule says that if f of x is positive, meaning the graph of the function lies above the x-axis, then its integral will also be positive. I think this is very clear. Why? Because when the curve is above the x-axis, we already said that the area under it is considered positive. So its integral must be positive. Is the converse also true? Does that mean if an integral is positive, then the curve must necessarily be above the x-axis? Excellent. No, it is possible that one part of the graph is above the x-axis and another part is below it. If the positive area is much larger, then the overall integral becomes positive. So if a function is entirely positive, its integral is necessarily positive. But if a function is not entirely positive, meaning some parts are above the x-axis and some parts are below it, the integral can still be positive. It is also possible that its integral may not be positive. Now, for the next rule, if f of x is less than g of x, or at least on the interval from a to b, f of x is smaller than g of x, what does that mean? It means the graph of f of x lies below the graph of g of x on that interval. So in this case, what happens? Excellent point. Its integral will also be smaller. Why? Because when the function itself is smaller, the signed area under its graph is also smaller. That's right. Now, let's move on to the first fundamental theorem. We actually have two fundamental theorems. The first fundamental theorem of integral calculus and the second fundamental theorem of integral calculus. This is a very, very important theorem. The first part of the first fundamental theorem is what we call the derivative of an integral. Our goal is to differentiate an integral function, especially one whose limits are variable. What exactly does this mean? Just look at what the rule says. It says we have an integral from u of x to v of x. You see the limits of integration of variable functions. If we want to take the derivative of the integral of f of t dt with limits from u of x to v of x, that means we want to differentiate an integral, but both the upper and lower limits are variable functions. So what is the rule? The rule says first differentiate the upper limit. So we get v prime of x. Then in the function f, instead of t, we substitute the upper limit itself, v of x minus. Now, do the same thing for the lower limit. Take the derivative of the lower limit and we get u prime of x. Substitute u of x into f. Excellent. Now what's next? It's time to solve an example. Let's go through the first example together. We have the integral from x squared minus 1 to square root of x of t squared plus t dt. I want to take its derivative. What was the rule? Yes, the derivative of the upper limit, square root of x, is 1 over 2 square root of x. Well done. But no, now substitute square root of x itself in place of t. You're substituting its derivative. I told you don't make that mistake. Substitute the original upper limit. Square root of x is raised to the power of 2. So we get x plus square root of x. Then we subtract the lower limit part. The derivative of x squared minus 1 is 2x times the function with x squared minus 1 substituted in place of t. Excellent. We made the substitution and the result was obtained very easily. Here's another example. Consider the integral from sine x to cosine x of square root of t dt. You can calculate its derivative yourselves. It's based on the first derivative rule, you see. Yes, that's right. We take the derivative of the upper limit and substitute the upper limit itself directly into the function. That's absolutely correct. Minus the lower limit part. We take the derivative of sine x and substitute sine x itself into the function. Well done. So the final answer is negative sine x times the square root of cosine x minus cosine x times the square root of sine x. Let's solve one more example to make sure this is really settled in. Everyone, try it on your own first. The difference from the previous example is that t and x have switched rows. That doesn't matter. We differentiate the upper limit, substitute the upper function into the integrand, then subtract the lower limit part. This time, since the lower limit is constant, its derivative is 0. So you don't need to write the lower limit part, just use the upper limit part. Excellent, let's continue. Okay, we studied the first fundamental theorem. So what was the first fundamental theorem? The first fundamental theorem showed us how to take the derivative of a definite integral. The second fundamental theorem is even more useful. Now we want to see how a definite integral actually calculates area. The second fundamental theorem states this. If capital F of x, pay close attention, if capital F of x is an antiderivative of small f of x, or as we said before, if capital F is the result of integrating small f, then we can use it to calculate the definite integral. Well done! It states that the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. Now, think about what this means. It says that if you want to find the value of a definite integral, your first step is to calculate the indefinite integral, just like before. Once you have the result of the indefinite integral, first substitute the upper limit, excellent, then subtract the value at the lower limit. Upper limit first minus lower limit. Okay, I'll start with a very simple example so we can practice together and understand the concept. Then we'll solve more difficult examples together. We're talking about the integral from -2 to 3 of 2x minus 5 dx. What does that even mean? Conceptually, 2x minus 5 is just a line, isn't it? So if we draw this line, what would the area under it be? You might say, come on, for a simple line, we don't really need integrals. Yeah, you're absolutely right. I started with a very straightforward example. Your main goal is to understand the core idea first. Basically, we're asking, what is the total signed area between this line and the x-axis? Okay, the rule says that we must integrate this first. We have 2x minus 5. You should already be able to calculate this integral easily. So according to the rule, the antiderivative becomes x squared minus 5x. Now, what does it tell us to do? First, substitute the upper limit. That gives us 9 minus 15. Then minus. Now substitute the lower limit. That gives us 4 plus 10. So what is the final answer? What does -20 actually mean? It means that the signed area between this line and the x-axis is -20. Now let's look at a better example. What does the integral from -pi over 2 to pi of cosine 3x dx actually represent? It represents the signed area between the cosine curve and the x-axis. I'm sure all of you are familiar with sine and cosine functions. But remember, these curves are not made of semicircles. If you look closely, if they were semicircles, their diameters would have to match the width of the graph, and that does not work here. So they are definitely not semicircles. Before definite integrals, we could not really find the exact area under curves like these. Now, based on the rule, what should we do? First, we integrate cosine 3x. By the rule, it becomes 1 over 3 times sine 3x. And then what did we say we should do? First, substitute the upper limit, yes. Then minus and substitute the lower limit. Everyone should already know sine and cosine values, all right? So when x equals pi, sine of 3 pi is 0. Sine of -3 pi over 2 is 1. So after substituting the limits, the result becomes -1/3. All right, let's move on to the next application of definite integrals. Let's discuss the mean value theorem for integrals. So what exactly does this theorem say? It says that if f of x is a continuous function on the closed interval from a to b, then there exists at least one number, which we call c, in the open interval from a to b, such that f of c is equal to the definite integral of f of x from a to b divided by b minus a. We call this value the average value of the function, or the mean value of the function. So if we are asked to find the mean value of a function, that means we need to take its definite integral from a to b and then divide by b minus a. Let's solve an example. Consider the function f of x equals 3x squared minus 2x on the interval from 1 to 4. So we are given a function on the interval from 1 to 4. What is it asking for? Part A asks for the average value. It asks, what is the average value of this function? Okay, this is very straightforward. What is the formula for the average value? The formula is the definite integral of the function divided by the total length of the interval. Now, let me clarify one thing here. We spent 6 parts, 6 full sessions, learning different methods of integration. And why did we do that? Because if you truly understand indefinite integrals, and if you really learn the techniques of integration, then definite integrals mainly become a matter of substituting numerical values. All right, let's go ahead and solve this. I could have given you a very complicated function for f of x, and then calculating its indefinite integral would take a lot of time. But here, we are using simple functions so you can clearly understand the difference between definite and indefinite integrals. We take its integral from 1 to 4 and then divide by the length of the interval. So we have 3x squared minus 2x. Okay, we integrate. The integral of 3x squared is x cubed, and the integral of minus 2x is minus x squared. Then we evaluate it from 1 to 4. As I already mentioned, first we substitute the upper limit, 4. Then we subtract the value at the lower limit. And finally, we divide everything by 3. This means the average value, or the mean value of this function over the interval from 1 to 4 is equal to 16. Yes, let's move on. In part B of this same question, it asks for the number c. So we found the average value first. I explained that f of c represents that average value. Now the problem is asking for c. In other words, find the point where the function reaches the average value, which is 16. So f of c is equal to 16. So f of c means we substitute c in place of x in the function of x. I put c into the function and we get 3c squared minus 2c equals 16. Then two values for c are found. One of them is 8/3, which is inside the interval. The other one is not in the interval. Our interval was from 1 to 4, so the other root, which is -2, is not useful for us here. Let's move on to another example. I'll give you some time now to solve this example on your own. What exactly is this question asking for? It is only asking for the value of c. Be very careful here. In this question, it asks for c, but you still need to find f of c first before you can determine c. Everyone, grab your pens. You are expected to solve this yourselves. If you can't solve it, don't look at the answer right away. So, what did you do? Were you able to solve it? Good for you. Why not? Where are you stuck? I see. All right, come with me now. Stay with me and I'll show you what I did. Everyone, please follow along. Let's solve this together, just this one time. It asks for the average value. So f of c equals the integral from -1 to 2, since the interval is from -1 to 2. Does it matter whether the interval is open or closed? No, it makes no difference here. So we take the integral from -1 to 2 of 1 plus x squared divided by the interval length, which is 3. Now everyone should integrate this. X plus x to the power of 3 over 3. We substitute the upper limit first, which is 2, then subtract the value at the lower limit. All right, the additions and subtractions are very simple now. We get 2. For those students who couldn't continue from this point, yes, exactly, this is f of c. Now you have to find c, right? Well, didn't the problem give you f of x? And didn't you just find f of c? So substitute c into f of x. Putting c into f of x gives 1 plus c squared. Set it equal to the number we found, which is 2. So c is plus or minus 1. But remember, c must be inside the interval. -1 is not inside the open interval. It is actually the starting point of the interval. So it is not useful for us here. Okay. So at this time, in this problem, we are given the average value of the function. It says, I will give you the average value myself. We ask, how much is it? It says it is 2/3. Then we ask, all right, what exactly do you want from us? You have already given us the function, and you have also given us its average value. So what are you looking for? It says this function is defined on the interval from 1 to b. Now the problem asks us to find the value of b. In other words, it wants us to determine the interval over which this average value was calculated. The method is still the same. We know the formula for the mean value of a function. We'll apply the formula and see what we get. So we have the integral from 1 to b of 2 over x squared dx, all divided by b minus 1. Well, the integral of 2 over x squared is very straightforward. Everyone can calculate this integral. 2 over x squared means 2 times x to the power of -2. We said, according to the rule, we add 1 to the power and then divide by the new power. So we get 2 times x to the power of -1 divided by -1. That means -2 over x. From 1 to b. First, we substitute the upper limit, -2 over b, then minus the lower limit value, which is -2. So it becomes -2 over b plus 2, and then we divide by b minus 1. This is the average value, and the problem says this average value is 2/3. Then, by cross-multiplying, we arrive at a quadratic equation. Exactly. Well done. We need to find b. Okay, we found two values for b. One of them is 1 and the other is 3. The value b equals 1 is clearly not acceptable. Why? Because if b were 1, the interval would be from 1 to 1. That means the interval length would be 0, so it cannot be used here. Let's move on to another application of the definite integral, and that is finding the area between two curves. The area between two curves. We've already discussed how a definite integral calculates the signed area under a single curve. But how does it actually calculate that signed area? It counts the part above the x-axis as positive and the part below the x-axis as negative. This is the rule for definite integrals. But enclosed area does not work that way. For enclosed area, even if the region is below the x-axis, we still report its area as positive. In other words, for enclosed area, we want the actual total area of the region. So the difference between a definite integral and enclosed area is exactly this. For enclosed area, we always consider the area positive, whether it is above or below the x-axis. But in a definite integral, the part above the x-axis is positive and the part below it is negative. Exactly. Now let's see what we do for enclosed area. What is the first type of enclosed area? It says that if on the interval from a to b, the function f of x is greater than the function g of x, then the area enclosed between these two functions is equal to the integral from a to b of f of x minus g of x dx. We have two curves. So what is the area enclosed between these two curves? It is the integral from a to b of f of x minus g of x dx. Now what if I cannot tell whether f is above g? What if I don't want to get involved in drawing the graph? What should I do? Nothing special? You simply write f of x minus g of x inside an absolute value. The absolute value takes care of everything. What does it do? It turns any negative value into a positive one, and it leaves positive values unchanged. So let's go and see what that really means. Example, find the area enclosed between the curve e equals x squared and the line y equals x plus 2. All right, to understand this topic better, let's sketch the graphs a little. Let's visualize them. Let's see exactly which area we want to find. So what do? First, I explain where this enclosed region comes from. It comes from the intersection of the line and the parabola x squared. So I set the equation of the line equal to x squared. This gives us two x values, -1 and 2. We marked clearly on the figure that the region we want is from -1 to 2. Now I need to find the enclosed area between these two curves. What was the formula for enclosed area? It was the integral of the difference between the two functions. We are looking at the graph right now, and it is clear that the line is above the parabola. But even if you did not see the figure, it would not matter. You could simply put an absolute value around the difference. As you can see, we also wrote the difference here. X plus 2 minus x squared. Now I already know how to calculate indefinite integrals. I'm going to take the integral in the usual way. You can see it becomes x squared over 2 plus 2x minus x cubed over 3. Then I'll substitute the upper limit and subtract the value at the lower limit. The rest is just addition and subtraction, which I'll leave for you to complete on your own. Let's move on. We'll solve a better example. All right, let's move on to the next example. We have the enclosed area between two curves, and this time both of them are parabolas. One of them opens upward. As you can see, this parabola is x squared minus 2x plus 2. And the other one is a downward opening parabola. To make it easier to understand, I recommend that you sketch the graphs so you can see exactly what area we are trying to find. Well, we all know how to draw a parabola. We've learned several methods for that. You can draw it using the vertex or by completing the square. I'll leave the actual drawing to you. I drew the two parabolas to find their points of intersection. So I set their equations equal to each other because I need the intersection points. Why? Because the figure clearly shows that the region goes from the first point of intersection to the second point of intersection. That is the area enclosed between these two curves. So if we want the area enclosed between these two curves, we take the integral from 0 to 3 of the difference between them. Since we have the graph, it is clear which function is on top. But even if we didn't have the graph, it still wouldn't be a problem. As I mentioned, we write the difference and put it inside an absolute value, so the enclosed area does not become negative. Okay, we subtract the two functions first. What remains is negative 2x squared plus 6x. So the integral becomes negative 2 times x cubed plus 3x squared. First, substitute the upper limit. Here, the lower limit is 0. In the end, the answer is 9. That means the area enclosed between these two curves is 9. Is everyone ready? That's fantastic. So let's move on to the next example. This time we are given a specific figure. The problem itself gives us the shape, and our task is to find its enclosed area. What does this figure contain? It includes the square root of x function and also a straight line. I'll give you a moment to work on this. Then we can check our answers together. Well, thank you for the time you spent on this. Bravo. I can see that you're slowly but surely getting the hang of it. You're even calculating definite integrals. The given figure, the enclosed region starts at x equals 0 and ends at x equals 4. What am I going to do? I'll take the integral from 0 to 4 and then subtract that white region. And can you tell me what created that white part? Exactly. Well done. And what did that line create? What kind of shape is it? It is clearly a triangle, isn't it? So we can calculate the area from 0 to 4 and then subtract that triangle. We need to subtract the area of that triangle. What is the area of the triangle? It is base times height divided by 2. The area of that region is 2. We also calculate the integral from 0 to 4 of square root of x. After substituting the limits, it becomes 16/3. Then we subtract 2. This gives us the area of that hatched region. Now, let me point out a subtle detail here. Notice that this hatched area is not simply the area between two curves. What does that mean? Look, right now in this particular figure, the x-axis has actually come to our assistance, and that x-axis all on its own has effectively closed off one entire side of it. What does that mean? The formula I told you to use, the integral of the difference, applies when the two curves themselves create a closed region. This is a very subtle point. How do we know? I always tell my students to do this. Imagine that the hatched region is filled with water. Tell me, if I remove the x-axis and the y-axis from this figure, will the water inside the hatched region spill out or not? In this particular shape, if I remove the x-axis, then the whole region, if it were filled with water, would simply pour out. But to visualize this better, look at the figure from the previous problem. If the area between those two curves were filled with water and you remove the axis, nothing would happen. The water would stay right there between the two curves. So that problem was truly about the area between two curves. This time we're going to find the area between the curve x equals y squared and the vertical line x equals 4. Notice that x equals y squared is not written as a function of x. This is actually our first example where the curve is not given as y equals f of x. You can clearly see the curve x equals y squared. I'll sketch its shape, and we'll also consider the vertical line x equals 4. We can solve this problem using two different methods. Yes, we can solve it in two ways. Let's begin with the first method. Take a look. This figure has two parts. One part is above the x-axis and the other part is below the x-axis. So if we have y squared equals x, what happens when we take the square root of both sides? Y equals plus or minus square root of x. When we take an even root, we get plus or minus, right? So y becomes plus or minus square root of x. The positive branch is above the x-axis and the negative branch is below the x-axis. So what can I do? Since the figure is symmetric, I can calculate the upper part and then multiply it by 2. What does the upper part mean? I take the area under y equals square root of x from 0 to 4. All right, let's calculate. The integral from 0 to 4 of square root of x. That becomes 2/3 x to the power of 3/2. Now you can see that I multiplied it by 2. Why? Because as I explained, the region consists of two symmetric parts. Now I'll substitute the upper limit. Then we subtract the value at the lower limit. Well done. This is how we calculate the area of the shaded region. This is one way to do it. There is another way. So let's look at the second method. Let's see what we do in this second method. You see, up to now, we have usually calculated area with respect to x using dx. What does dx mean here? It means we are slicing the region vertically. Now, what can we do? This time, we can use the y-axis instead. What does that mean? I should say, look, the shaded region is the area between x equals y squared and x equals 4. So, instead of using dx and instead of writing y as a function of x, we write x as a function of y. This way, we can calculate the area using dy. How do I write the enclosed area as an integral? Well, from where to where does y change? From -2 to +2. So I can write the integral from -2 to 2 of 4 minus y squared, or y squared minus 4. It doesn't matter if we put the difference inside an absolute value. And then, very simply, we take the integral. It becomes 4y minus y cubed over 3. Now substitute the upper limit, then subtract the value at the lower limit. The same area we obtained with the first method, we obtained here as well. Now we're going to find the area enclosed by three curves. What curves are given here? We have x equals y cubed, y equals x squared, and y equals 2 minus x. You can sketch all three of these curves easily. Since this is the very last type of problem we're going to solve in this section, I want to give you a good chance to think about it yourselves. So please take a moment and think it through. draw the three curves. Then see how you can find the area between them. Everyone, grab your pens and let's begin. Okay, thank you for the time you spent on this. It may have been a bit difficult, but that's okay. We'll solve it together. One problem students often have here is that they don't even know where the enclosed region is. Where should they look for it? Where should they shade? This is the enclosed area you see. If I draw these three curves for you, the graph of y equals x squared is very clear, and we have already drawn the straight line as well. And x equals y cubed actually means the same as y equals the cube root of x, whose general shape we are all familiar with. Which region is it? It is the region where no matter which direction you move, you eventually hit one of these three curves. In other words, you should shade the region that is blocked by these three curves from all sides. Neither the x-axis nor the y-axis. Excellent. The shaded region is clear in the figure. All right, now to find the enclosed area, I need to find the intersection points. So how did we usually find intersection points? We set the curves equal to each other, right? Now set the cube root of x equal to x squared. What will x be? 0 and 1, well done. Now set the line equal to x squared. So set 2 minus x equal to x squared. This gives us a quadratic equation. What x values do we get this time? 1 and negative 2. All right, now look, what is the issue with this enclosed area? Pay close attention to what I'm saying. Just look at x squared and the line. I mean, if the cube root curve were not there, what would the area between x squared and the line be? That white region would also be included, the white region between those two curves. I mean, if the cube root curve did not exist, we would simply write the integral from negative 2 to 1 for the area between these two curves. And how would we find that area? Didn't we say it is the difference between the two curves? So I'll say it one more time. To find this area, I can first take the integral from negative 2 to 1 of the area between the two curves. That means I take the integral from negative 2 to 1 of the difference between these two curves. Now, which part is it that I don't want? I don't want that white region. Do you understand how I can remove that white piece? I'm asking, what created that white piece? That white piece is the region between the cube root curve and x squared. I'll calculate that part as well and subtract it from the larger area. That was interesting, wasn't it? So what exactly did I do? First, I found the area between the two curves. Then I realized there was an extra piece. So I found that extra piece as well. Then we subtracted the extra piece from the larger area. Let's move on. You can see the calculations here, but since they are very simple, I will skip them and move on to the next application of the definite integral, which is the last one I will cover for you. There are many more applications, but since they are all based on these ideas, we won't study them separately. The last application we want to study together is arc length. What does that mean? Well, if I have 2 points, I can easily find the distance between them and get the length of the line segment. But how do we find the length of a curve? Let's find the arc length of a curve together. The formula is the integral from a to b of the square root of 1 plus f prime of x squared dx. Using this formula, we can find the arc length of a curve from A to B. This means that if we are good at integration, we just substitute into this formula and the arc length is found. Now, let's take an example. The arc length of the function square root of x cubed on the interval from 0 to 4. So what does the formula say? It says the integral from 0 to 4 of the square root of 1 plus the derivative of square root of x cubed squared dx. We can write square root of x cubed as x to the power of 3 halves. What is its derivative? The exponent comes to the front and we subtract 1 from the exponent. So we get 3 halves x to the power of 1 half. So f prime of x becomes 3 halves square root of x. Now let's square this. Under the radical, we just need to expand that square. It becomes 9/4 x. So we get the integral from 0 to 4 of the square root of 1 plus 9/4 x dx. We can use substitution. That's fine. So I'll use substitution. If I set 1 plus 9/4 x equal to u, then its differential becomes 9/4 dx equals du. Now we substitute. it becomes 4/9 times the integral from 1 to 10 of square root of u du. Then we integrate square root of u, and after that we substitute the limits. It's very easy. The result of the integral is obtained, but be careful. After you use substitution and integrate, when you want to substitute the limits, you have two choices. Either convert the limits to u or replace u with its original expression and then substitute the x values. So keep in mind that the original limits are in terms of x. Don't just plug those numbers into u. Those numbers belong to x. So either convert the limits to u or replace u with the expression you chose in terms of x. Well done. One more. Find the arc length of the curve negative square root of 9 minus x squared on this interval. What was our plan? We used the arc length formula, the integral from negative 3 to 3 of the square root of 1 plus the derivative of negative square root of 9 minus x squared dx. I think everyone knows how to take this derivative. Now, substitute the derivative and square it. Yes, replace the derivative in the formula. Very good. Then we can simplify it a little. After simplifying the derivative squared, we get 1 plus x squared over 9 minus x squared. Now, let's simplify this and move on to integrating. So, after taking a common denominator under the radical and simplifying, it becomes the square root of 9 over 9 minus x squared. I can write the square root of 9 in the numerator as 3 and bring it outside the integral because it is a constant coefficient. What remains is 1 over the square root of 9 minus x squared. Remember this from the very beginning when I taught you this form? You are much more knowledgeable and professional now than you were back then. You can say with your eyes closed that the integral of 1 over the square root of 9 minus x squared is arcsine of x over 3 with a coefficient of 3. Now we substitute the upper limit. It becomes arcsine of 1. Arcsine means what angle has a sine value of 1, or better, what is the first angle whose sine is 1, pi over 2. Then minus, now we substitute negative 1. What angle has a sine value of negative 1? Negative pi over 2. We do the addition and subtraction very easily. And with that, the lesson on definite integrals is finished. This was part of the Math is All You Need tutorials, and now it has come to an end. I would love to hear your thoughts on this episode and also on other math topics you think we should cover. We are already preparing other areas of mathematics for you, such as double integrals. What a challenge! Just like complex numbers, integrals help you understand how complex numbers can enter mathematics in a meaningful way. I would love for you to tell us if there are any difficult topics that we haven't covered yet. We will try to prioritize them in future videos. Please subscribe, like, and leave a comment on our videos. I hope this series has helped reduce some of the frustration you may feel with integrals. And I hope that in future episodes we can continue this journey together so you can see and feel how beautiful math becomes when we become friends with it. And remember, math is all you need.